Hello everyone, my name is João Parente. I'm from the University of Parente here in Portugal, and I'm going to introduce my work, which is called the hybridization effect on the mechanical and piezoresistive behavior of epoxy nanocomposites. So first, an outline of my work. I will start with an introduction and objective, followed by the materials and methods used for this work in particular. Then I will show the results for nanocomposites and results for composite laminates, and finally a conclusion. Going to an introduction. Epoxy composites are used in various industrial applications due to their good mechanical properties. These materials are composed of a polymeric resin, usually an epoxy-based resin, and a reinforcing material such as carbon, glass, aramid, or natural fibers. Nowadays, there have been many applications using nanoparticles due to their unique surface effects, increased chemical activity, and physical properties. Among these nanoparticles, graphene and carbon nanotubes are one of the most promising due to its excellent mechanical and electrical properties. The addition of these materials to the matrix of the composite material should improve the mechanical and optical properties of the composite material to which they are added. So graphene is a material composed of carbon atoms in a sp2 configuration connected in an hexagonal configuration. They are usually produced from the exfoliation of graphites, can be functionalized into several different compounds, and are usually mixed or added to the matrix of the composite material it's going to be improved. It can be divided into three groups: graphene nanosheets, graphene oxide, and graphene nanoplatelets. Carbon nanotubes are similar to graphene, but their configuration is tubular instead of a sheet. Similar to graphene, they have exceptional mechanical and electrical properties and are divided into two groups: single-wall carbon nanotubes and multi-wall carbon nanotubes. So the application of these nanoparticles in composites has many applications, especially in the areas of aeronautical, aerospace, railway, automotive, military, and nautical industries. So taking that into account, the objective of this work was to study the effect of the nanoparticles on the mechanical response of a nanocomposite and a composite laminate, analyze the influence of the hybridization of both these nanoparticles on the mechanical properties of the composite and the laminates, and investigate their influence in the electrical response through electromechanical tests. So moving to the materials and methods. So for this work in particular, we used low viscosity epoxy resin, two-component epoxy resin from Sicomin, and for our laminates, use a glass fiber. For our nano-reinforcements, use graphene nanoplatelets, which are more commonly available, and multi-wall carbon nanotubes, which are also very used in the industry. For this work in particular, we use three types of hybrid compositions: 50-50, 0.5 and 0.25 of either graphene or carbon nanotubes, which I will explain later. And we also investigated single use of a single nano reinforcements from 0 up to 1. To fabricate our laminates, the process was similar to both. In the case of the laminate, first we had the mixture of our components for 3 hours at 1000 RPMs, so mixing our resin with our nanoparticles with ultrasound assistance. For the fabrication of the laminate itself, we used 20 layers of glass fiber, and you fabricate it through the traditional hand layup method. After that, you cure the laminates for 24 hours at room temperature using pressure and vacuum to remove the air bubbles, and then followed by a post-cure for 24 hours at 40 degrees. As for the nanocomposites, the first process was the same as the laminate, which is a mixture of the components. After that was the filling of the molds for also 24 hours at room temperature, and the same post-curing process for 24 hours at 40 degrees. For the mechanical tests, you perform 3-point bending tests at a displacement rate of 2 millimeters per minute, and you also perform cyclic bending tests. After the tests, you took a microscope image and same images. For the piezoresistive tests, use silver paint to paint the electrodes. These electrodes had a size of 2.5 by 10 and were separated by each other by 25 millimeters and were painted on the surface of our sample, on the top and on the bottom. To perform the tests, the piezoresistive tests, we apply the load using our the same equipment used in the bending tests, and you measure the resistance through a digital multimeter. After these tests, we also determine the gauge factor and the surface resistivity through the formulas presented here. So, moving to the results. So, we first started by studying graphene. So that's why we use 0 to 1%. And we concluded that 0.75% of graphene show the best bending stress results, as well as the bending stiffness results. As for bending strain, as predicted, 1% show the best results. So, taking this into account, use this as the basis for our following studies. So, analyzing the mechanical properties of the hybrid reinforcement in nanocomposites, we can see that although 0.75% for graphene was the best quantity that was the quantity that achieved the best results, for carbon nanotubes, 0.5 show the best results. But hybridizing both components, meaning mixing the two, showed better results than using either single one of them, with 0.25% of carbon nanotubes and 0.5% of graphene showing the best results, both for bending strength and bending stiffness. For bending strain, the 0.375 showed the best results. Analyzing these results as synergy, you can see that all hybrid mixtures have a synergetic effect, which can be seen here. They are above the line, and therefore they're good. So moving to the cyclic tests, as said before, we put electrodes on the top and on the bottom. As you can see, on the left, the signals from the top, the placement of the electrodes on the top showed a more clear signal compared to placing the electrodes on the bottom of the specimen. But both were able to be measured. Also take into account that placing the electrodes on the top had an opposite response compared to placing it on the bottom. This means that as you apply the load, the resistance signal decreased, while placing on the bottom, the resistance signals increased. So therefore, of these two, we choose the top electrodes as for the following tests. So after analyzing all tests, we concluded that the using of a hybrid mixture showed lower resistivity results compared to the use of only one nanoparticle. In this case, I'm showing here only nanotubes, since graphene we are not able to measure in our equipment, and calculating a gauge factor, which determines how sensible the material is to the load applied. You can see that the mixture of 0.25% of graphene and 0.5% of carbon nanotubes show the best gauge factor results. Also taking into account that as the cycles increase, there was an increase on the gauge factor, which can be related to the stabilization of the signal throughout the cyclic tests. We also perform incremental force and incremental relaxation time tests, and as you can see here on the left, as we increase the load, the maximum load applied, we can see a reproducible signal, resistance signal in our nanocomposites, which means that this material can reproduce increasing loads. Also, showing a relaxation time, incremental relaxation time, we can see that as we apply the load, we can detect when this load is applied, and as we increase the relaxation time, you can see that the material has a tendency to relax. So moving to the laminates. So taking into account all the results, we also perform bending tests for the laminates, in this case glass laminates, and you can see that the best results for the single components were 0.75% for both. But also using the hybrid laminates also resulted in better results, bending stress results, with 0.375% of both components achieving the best results. This is true for both bending strength, bending stiffness, and bending strain. As for synergetic effect, this quantity, 0.375 of both components, was the only one that really showed a good synergetic effect. So the macroscopic and SEMS images, we can see as we applied nanoparticles in our laminates, you can see that there was a clear appearance of deflections throughout our specimen, and through the SEM images, we're also able to detect the presence of carbon nanotubes, although our equipment was at its limits. The presence of carbon nanotubes and graphene nanoplatelets in the matrix of our specimens. So moving to the cyclic tests. For the cyclic tests, we see that the using of a laminate showed a way more linear results compared to nanocomposites, as you can see here in the images to the left, and the gauge factor did not change throughout the cycles. Also, similar to the previous results, the use of a hybrid mixture showed lower surface resistivity, and the sample containing 0.375% of both quantities showed the best gauge factor results. Also did studies on increasing stabilization time, as did previously, and stress plateaus, and similar to the previous results, you can detect when the load was being applied. The difference here is that the signal was way more linear compared to the nanocomposite. For the stress plateaus, we're also able to detect the plateaus, although as expected, the behavior was the opposite. And we're able to see the stabilization of the signal as the time went on. Also did progressive stress increase and progressive loading rates tests, and similar to nanocomposites, we can see the increase of the electrical signal with increasing loads, and with the progressive loading rate, which means speed. You can see that as we increase the speed of the test, this increasing speed was also able to be seen in our resistance signal. So to conclude, through this work, we can conclude that incorporating hybrid mixture involving 0.5% of graphene and 0.25% of carbon nanotube lead to the optimized bending properties. The placing of electrodes on the top of the specimen leads to a clear resistance measurements. Higher carbon nanotube contents in hybrid nanocomposites results in higher gauge factors. And for glass fiber laminates, the samples with hybrid mixture of 0.375 achieve the best bending strength and piezoresistive results. And these results demonstrate the possibility of monetization of the structural health of nanocomposites and the composite laminates. So I want to thank FCT and GraphNest and GraphNest especially for providing our graphene news and this work. So that is all. I'm ready for your questions. So thank you.